So today we are going to start discussing a new topic. It's basically going to be about functions which are taking value in the vectors. But before we start this discussion, let me just tell you a few remarks about the some general remarks basically. Okay, so check your emails regularly, and in lecture notes or in the videos sometimes there might be some typos in the file, and if you notice them, please tell me. I will correct it, and I will update the lecture note. What I will do is I will update the file and mark that correction or modification in a blue color text, okay, so that it will be convenient for you to follow. Yeah, it's more or less difficult to kind of find your own typos, so please be careful. Okay, so as I said, today we will start talking about these vector valued functions. So basically the idea is now we are going to develop some tools from the calculus. Okay, so you will notice that this section is basically using the knowledge of your real variable calculus, the MTS 101, and this knowledge helps you to basically develop the corresponding concepts of, for example, limits and continuous functions, and then derivative and so on for the vector valued functions. Okay, so you have to keep recalling some of the concepts from your MTH 101. Okay, that is very important. For example, the definition of continuous functions and limits and so on. Okay, so whenever you encounter something, you just go back and just recall few examples from there, and then you will feel comfortable. Okay, or you can just discuss during the tutorials. So vector valued functions, as the name suggests, basically it is going to involve vectors. Okay, so we have actually already seen an example of this, so we begin with that. Okay, so just recall when we started talking about the equation of line, the vector equation of line was given by this, isn't it, where this r0 is a fixed point p0, if you recall, and this is the position vector of that, okay, on the line, and then t is a parameter, and thus b defines the direction of the line. Okay, so this line, this is the vector equation of line passing through the point whose position vector is r0 and which is in the direction of vector b. Okay, so here this t is a real number and it's often referred to as a parameter. So basically what is happening here, you just notice it, that for each value of t I am getting a point on the line. Okay, so in a way, what is it telling me, or what is it doing? It is basically giving me a function which sends t to a vector or a point on the line, isn't it? So if I express this side depending on t and call it r of t in terms of function, what I have is basically and this, and then you just write down the components. So the components, each component, if you look at it, is going to look like this and this and this. Okay, so I can think of these components because this is a real number, this is a real number, this is a real number, so this is addition of two real numbers, and I can think of it as a function of t and giving me, so this ft, what does it do? Ft sends t to this, which is again a real number, so f is a function from r to r. Similarly g and h. Okay, so this function of t has got these three component functions, and precisely this is what the vector valued functions are going to be. Okay, so such a function is referred to as a vector valued function. Okay, so more precisely we just write down the definition on record. So a vector valued function is a function, okay, such that it has its input as a real number. So this t, the parameter t, is the input, or so the domain of this function is a real line. Okay, or it can be a subset of real line, and output is going to be a vector. Okay, so we are always going to write the notation t going to rt or t going to ut or vt, for vector valued functions. And when I have this, so rt is going to have the three components, each component function I will get, and they will be functions from r to r, and we will often write these functions as f, g and h. okay. And if you want to write in terms of I, j and k this vector, the ft, the coordinate of I is going to be ft and so on, okay. So this is how you can always express a vector valued function in terms of component function. So if you recall, the idea of function from R to R is basically being generalized to define vector valued functions. So in a way, there is nothing new in terms of the new concepts, okay. Because what we are going to see that the information about f, g and h is going to determine the vector valued function R, isn't it? Okay. So another term here we will use the graph. So graph of a vector valued function is going to be basically the set of all terminal points. So t going to rt, so rt is a vector. So you look at the terminal point of the vector, when that is expressed as a position vector, okay. So the collection or the set of all such points, the terminal points, is going to be called the graph of that vector valued function, okay. Now since for vectors we have seen that the addition and scalar multiplications is done as according to the components. So similarly you can define the sum of two vector valued functions r1 and r2 and call this as the sum of the vector valued function. And what is it going to be? Just the sum the corresponding components, okay. And similarly scalar multiplication, if the scalar gets multiplied in each of the component, okay. So basically what we have, we will definitely need some knowledge of functions from R to R to understand the vector valued functions, okay. So just a few examples we can look at. The first example is the example which we started with. I have given some particular values. So here rt, I am taking the t comma t comma t. So this is a line passing through the origin and having the direction given by the vector 1 comma 1 comma 1, isn't it? So here f, g and h you write they are all the same, and this gives you a vector valued function, isn't it? So you can basically try to plot the graph. You can find out all the terminal points. And the second example is slightly different. In the first coordinate it is varying according to cos theta or cosine of t, and the second component is sine of t, and then third one is t. So here f is cosine, g is sine, and h is just t, okay. And if you try to visualize this, what is it going to be? I have put the picture over here, but let us see that why is it so. So for any t you take, the first two guys, the cosine and sine, their square sum up to 1, okay. So t is basically is going to give you the height, and the first two coordinates are telling you that this is at that height t, the point x comma y lies on the circle, isn't it? So this is how it is going to go. So this is like a coil or a spring, whatever you may call it, and in this language it is called a helix, okay. So it's a very important example. It apparently it has got a lot of applications. It appears naturally in the study of DNA and so on. I will not go into that because I do not really know much about it, okay. So what I'm trying to say here, that one can try to visualize that what graph I am going to get out of a vector valued function, okay. So just just draw few points, take particular values of t like 0, and since cosine and sine are there, so take the values in terms of pi, okay, like pi over 4, pi over 3 and so on, okay, and then draw some particular points, okay. So this is how we so basically what is happening, that the parameter t is being sent to a vector via this function, and we are going to refer to it as a vector valued function, okay. We will study a lot of properties, and in today's lecture mostly it is going to be just analogous definitions from your calculus 1 course, like the definition of limit and then continuity and even derivative, and you will see that everything just is being done in terms of the usual derivatives which we already know. So in a way not much is new in this, but there are going to be ideas which will be developed further, and we will see that you do get new concepts, okay. So let us define what do we mean by a limit. Now this often becomes a problematic part in calculus 1 when somebody talks about the epsilon delta definition. So don't worry about it, because you are already comfortable with that. And frankly speaking, we won't be using much of this approach. Often we will have functions which are already nice, like continuous and so on. I will define them, so you won't have to really compute a lot of limits and so on, okay? Because we will be, our goal in this course is to understand somewhat or develop the geometry also, along with the calculus. So when we talk about geometry, generally we take nice things, okay? So limit, because rt, so you take a vector valued function and it has got these three components, so you define the limit t going to a of rt, okay? Now you see that this side, this rt is a vector, okay? So we are talking about limit of vectors, and this is defined as limits of each component. So you take the limit in each of the components, and whatever you get, you call that as the limit, okay? So here there are two things. First, this is the limit of real numbers, or functions of real numbers. And when I write this symbol, right now this is just a symbol, okay? So you have to say that this limit exists, then only this makes sense, otherwise it doesn't make sense, okay? So here I have, just for convenience or for just to recall what is the definition of limit for real valued function, because that is what I need, and this side is just a symbol, isn't it? So this definition is given in terms of limit of each of the component, okay? And this is exactly the concept of limit which we already know, okay? So remember that if we have a real valued function f, the limit t going to a ft, we say it exists and is equal to a number L if what happens, that ft gets arbitrarily close to L when t approaches to the point A, correct? So in this language, how do we write? So you take any epsilon positive, okay? So this is basically going to measure the distance of ft with L, and if we should be able to find, for this epsilon we should be able to find a delta, okay, a small number delta, such that if the t is varying in a small neighborhood of A, okay? So this is neighborhood I am saying, because I have the point A fixed, so I am moving around the point A, okay? So I am actually going A minus delta to A plus delta, so that is a small neighborhood of A. So if this I can do, and I get that ft minus L is always less than epsilon, then we say that this function has a limit as t goes to A, and the limiting value is L, isn't it? So basically you are able to reach this when I approach A. This approach is happening from the left and as well as from the right side, okay? So it's basically the same concept which we have learnt in our calculus 1, okay? And with the help of this we can define the limit of the vector valued functions, okay? So now just recall your previous examples and then try to just see that here f, g, h, everything is very nice function, so you can easily compute. Similarly in the second example, all the functions are nice, cosine is nice, sine is nice, and t is nice, so you can easily compute. Now the third example here, this is an extra one. The first two functions are fine, this is ft equal to t and gt equal to t, but h of t is 1 over 1 minus t, okay? Now all of you know that as t goes to 1, so there is going to be a problem, correct? When t is approaching 1, in the denominator I am going to get a number closer and closer to 0, but it is in the denominator, so it's going to blow up, okay? So that will tell me that if I approach 1 from right or left, and then accordingly we will get this plus infinity or minus infinity, correct? If this guy is positive, that means t is smaller, that means you are approaching from left, you get plus infinity. And so basically what is happening here, the limit is not finite, okay, or it does not exist. So for one of the component function, limit t going to 1 does not exist, and hence we conclude that the limit t going to 1 of rt does not exist, okay? So this is how you need to look at the concept of limit, it's important that all the three functions should have the desired property, otherwise we can't conclude the corresponding property for the vector valued function. Okay, once I know the limit, now I can talk about the continuous function. Okay, so what is a continuous function? It's basically you start with a function and then you say that this vector valued function is continuous at t equal to a. So notice that sometimes I am calling vector valued and sometimes I am calling vector function. Okay, they are the same thing. So you say that this is continuous, that means the limit t going to a of this vector function exists, and it is precisely the value of the function at a. Okay, so the limit exists, okay, but that doesn't automatically mean that it has to be the value of the function. Okay, so basically this tells you two things, that the limit t goes to a of this vector valued function exists, and the function r is defined at the point a, and this limit is exactly equal to r of a. Okay, so this is again you have to go back and recall some examples. For example, sin x by x, those examples. So we know that as x approaches 0, this function converges to 1, isn't it? But at x equal to 0, if I have defined my value to be something else, then the function won't be continuous. Okay, so those kind of examples you have to recall and try to have the analogy with whatever examples we are going to talk about over here. Okay, so the two things are important. First of all, the function has to be defined at the point, and the limit should match with that. Okay, now if you go back to the previous slide and look at the problematic function over here, now as t goes to 1, as we saw that this is going to give you plus infinity or minus infinity, so limit does not exist. Okay, what you have to do is, if you want to include this function in the examples of continuous functions or not continuous function, we have to also define the value of r at 1. Okay, you can define any value, but when I say I define a value, that means it's going to be a finite number, because the the functions are from r to the vectors, so each component function has to take a finite value. So you will notice that even if I define anything, the resulting function is not going to be continuous at t equal to 1, isn't it? Okay, so this we will have some examples and more discussion about, in fact we will always be working with continuous function. All right, so when we have continuous function, I will also talk about its curve. Okay, the corresponding curve it gives rise to. So this will be called a curve in space or a space curve. So what you have a continuous function. Okay, often we will assume that the given function is continuous. Okay, so you look at the graph of this in the space, and that will be called a curve. Okay, so basically by continuous, because we don't want curves in pieces. Okay, because if r of at some point is not defined, then I am going to get a jump in the curve. Okay, so basically we are always going to consider curves, because we will be studying some properties of curves. Okay, and so on. So we will always assume that it has at least the continuity with it, and we will call it a curve. So whenever I am calling something a curve, automatically it should mean that the corresponding function, the vector valued function, is continuous. Okay, so that is the understanding we will always have, unless we mention it otherwise. Okay, and also when we talk about curves, we are always going to assume that the t varies over a finite interval I. Okay, like a to b. Okay, because we are not going to talk about the infinite curves. Okay, we will always have some finite curve, and then we will try to understand its various properties. Okay, we will come to various properties and so on. Okay, and you can go on and introduce the notion of derivative. Again, everything is happening just using the component functions, which are functions from r to r. So all these notions are very easy to relate to. So again, what you do, you take a function r, then the derivative is going to be always denoted as r prime or dr over dt, and how it is defined? It is defined as the limit. Okay, so you look at the difference of rt plus h minus rt, where h is small or going to 0, and take multiply it So this is a scalar multiplication. See, look at this. The upstairs, the numerator here is a difference of two vectors. Okay, so it's a vector, and this h is a scalar. So what I am doing basically, I am scalar multiplying this vector, isn't it? So if this limit exists, we say that the derivative of r at the point t exists. Okay, and this guy is referred to as the derivative of r. Okay, and as per our convenience, we will use either of these two notations. Okay. Now this limit, as we saw, we know the rule for the addition and the subtraction, and also we know the rule for addition or scalar multiplication of a vector function. So everything, this limit can be transferred to its components. So when I transfer it to components, I am going to get the derivatives of the corresponding components. Okay, so the derivative is precisely given in terms of the derivatives of its component functions. Okay, so again, it's not anything new in terms of concept, because everything is defined in terms of the known things, the f prime, g prime and h prime, which are the usual derivatives of functions from R to R, isn't it? Okay, so this is actually the definition, that R prime t exists if and only if the derivative of the corresponding components f, g and h, all they exist, and we say that this is differentiable vector function at the point t. Okay, so we are going to use differentiable or derivative of r, and then you can keep on this, continue this process. You can take the second derivative, you can take the third derivative, and everything is going to be in terms of the derivatives over here. Okay, now just let us see that what does this derivative do, what does it basically tell us. Okay, so the picture is important here, so I will basically here I have written that you assume that you started with a vector valued function for which the r prime t exists. Okay, and then let us see that what is the derivative telling us. Okay, so you take the vector function, so this is your position vector of position vector rt, and then you take small h. Okay, so you see that t is over here, and then h I'm basically taking on the right hand side, so that means I am taking let us say h positive here. So t plus h, and then I evaluate the vector valued function at t plus h, so I am going to get a vector this r of t plus h. So this is one vector, this is another vector, and then this vector is nothing but the difference, correct? So the vector over here, the r of t plus h minus r of t, is nothing but this pq vector, isn't it? Okay, and it is pointing in this direction given by this arrow. Okay, now when I multiply by this scalar, the vector direction doesn't change, and h is positive, correct? So it doesn't change. Otherwise, if h was negative, it would point in the opposite direction. So here I am taking h to be positive, so this points in this. Okay, now in order to understand the derivative, what happens, we have to allow this h to be smaller and smaller. Okay, we will make it go to 0. So what does it mean? That means this vector will be over here. If I take a smaller h, and then it will basically keep coming to this side, and then you will notice that this vector is going to finally point or eventually point in the direction given over here, isn't it? So basically what is happening, this is our curve, and I started with a point P on it, and then I started looking at this difference or this ratio. Okay, I should not call it a ratio because this is a vector, this is a scalar, so this is scalar multiple of this vector. And as h goes to 0, what is happening, this vector is coming closer to this vector, and the direction of PQ is coming or going to approach the direction given by this. Okay, so basically RT is nothing but, or r prime t is nothing but, it's basically going to point in the tangent direction. Okay, so you know what is the tangent line? Basically this, you draw a line on the curve touching the point, and so this r prime t is, for this reason it is also called a tangent vector to the curve C. Okay, so the r prime t is going to give you the direction of the tangent line. Okay, and this is called a tangent vector r prime t. Okay, so for a vector valued function, the derivative is a vector and it defines the tangent vector to the curve at a given point P. Okay, and you see that, you know, this, if I if I take h negative, then basically this r of t minus h is going to be on this side. Okay, and corresponding picture you can draw. Okay, so we have the tangent vector, but often, you know, when we talk about the direction, we just talk about the unit vector in direction. So the unit tangent vector we will consider, and it is defined to be the vector as capital T. So this will be the notation for the unit tangent vector. So this is basically, by definition, you divide it by the magnitude of the tangent vector. Okay, here you have to assume this, you know, otherwise, you know, we won't have the direction if it is a zero vector. Okay, so we assume that r prime t is non-zero, otherwise this won't make sense. Okay, so basically the r prime t is nothing but is the tangent vector, okay, or the direction of the tangent line. Okay, so this is geometrically you can keep in mind. Yeah, so and then various properties, they will follow immediately, because our vector r prime t is defined in terms of the derivatives of its component functions, which are real valued functions. So look at all these properties. So take two vector valued functions, and then take one scalar function or function which is from r to r, and assuming that's differentiable, because we are talking about properties of differentiable functions. Okay, so in the first property, what we have done, we have taken scalar multiplication of this ft with u. Okay, so what would it do? U is over here, so f will get multiplied in each component, isn't it? So if I take the derivative of this, I'm going to get this. Okay, this just follows from the Leibniz rule, I'll tell you. And if I take two vector valued functions u and v, take their dot product. Now notice that, you know, this side, this is a real valued function. Now t going to this dot product, u is a vector, v is a vector, but when I take the dot product, it is a real valued function. So this notation here, dy dt, is actually the usual derivative of real valued function. Okay, and then I get the derivative of first, dot product with the other, and corresponding term. Okay, similarly for the cross product. Now this side you have a vector, and then this derivative of the vector valued function. Okay, you will get u prime, and then v, and then u v prime. Okay, and if this is kind of the chain rule, if your t is varying according to some given function, and you want to take the derivative, then, you know, this will be the chain rule for the vector valued function. All right, now let me just give you proof of one, because all the proofs are just same, essentially the same idea. Okay, so let us just see. Okay, this is what we need all the time in order to prove this, that if I have two functions, I take their product, the derivative is satisfies this product rule, or the Leibniz rule. Okay, so this is what you just need to use. So in the case of first one, f times u is basically, in terms of components, is this, because for derivative, for limit, for continuity, all we need to go to the components. Okay, so this is what we do. So now you need to compute the derivative of each of these. Okay, in order to compute the derivative of this. So when I compute the derivative, I will just write it for one, I get this guy, isn't it? So similarly, you are going to get two terms from here, two terms from here, and then what you do is you collect the terms corresponding to f prime t, and then collect the terms corresponding to ft. Okay, so this is going to be two things, and then they will give you this f prime t and then ft. Okay, using the idea of scalar multiplication and the vector addition. Okay, and similarly you can prove all the remaining properties. So, you know, that is really not difficult at all. Okay, but in case you find something confusing, or there is some doubt, you please discuss it in the tutorial. Okay, so for example, I mean, again we look at the same curve, that helix. You can compute its derivative. So cosine is minus sine, and then sine is cosine, and derivative of t is 1, and then I can compute the unit tangent. Basically, how? This is r prime t, and divided by the norm, or the magnitude of the r prime t. Okay, so this is sine square plus cosine square plus 1 is square, so it's going to be 1 plus 1 square root, isn't it? So that is how you have computed this. And if you take any particular value of t, you will get the tangent, the unit tangent vector at that particular point. So what you do is, I suggest that you go back to the example where we had drawn the helix, okay, here. So you pick some points on this curve and try to figure out how this tangent is looking. Okay, you pick a particular value of t, so that is going to give you a point, and you already know what is the tangent, unit tangent. So you please try to draw over here. Okay, that will help in order to understand the idea. All right. So this is another example. So what I am now doing, okay, this is a different kind of example, or it can be thought of as a property. So you take vector valued function and assume it's differentiable, okay, and also assume that it is such that its magnitude is always constant. Okay, so when I say the magnitude is always constant, that means all these position vectors, they lie on the sphere centered at the origin with the radius c, isn't it? That is the meaning, because if all the vectors on a given curve having the constant magnitude or a constant length from the origin, then that means they lie on the sphere of the radius given by this constant. Okay, so we already what geometrically we are saying that we are taking a curve on a sphere. Okay, so what can we say about it? So now this means basically that the square is also a constant, and square I know that it is nothing but the dot product of the vector bits itself, isn't it? Now using the property of derivative in terms of the dot product, I compute the dot product. So when I compute the derivative of this dot product, I am going to get this term twice equals to 0, because this side is free of t. So basically what I got, that for this kind of curve which is of constant magnitude for each t, that the r prime t and r, they give you dot product 0. But this property, recall that what does it mean? This says that r prime t is orthogonal to rt, isn't it? So basically for this kind of curve, the tangent vector is always going to be perpendicular to the position vector of the function, isn't it? So you can draw this. So imagine a sphere and take a curve on that, and you take a point, and at that point the tangent is going to be orthogonal to rt. Okay, now I have given you a small exercise also here. This is basically one side, correct? Now I give you the converse. So think of how to formulate the converse of this statement. Okay, mainly basically what I am saying is that you start with a function and assume that this property holds. Can I conclude something like this about rt, isn't it? That will be the converse. So think about it, that is it only one way, or I mean the reverse direction is also going to be true. Okay, now in a similar fashion I can also define the integral. Okay, so integral, I am just going to define the definite integral all the time here. I am going to integrate the parameter, I mean the vector valued function with respect to the parameter varying over an interval. Okay, so everything, since it is in terms of components, so all these properties are just, or these definitions are just in terms of the components. So integral of this vector valued function, so this is just a notation and it has this meaning. This notation the definition of, similarly this So basically what you do, when you integrate a vector valued function, you get a vector, and that vector has the components which are integrals of the corresponding component functions. Okay, so this is how you are going to since everything is just in terms of component functions, so I am not writing too many examples, because and the properties like what will happen when I have integral from a to b and then c to d, you can figure out those things. And if I have two functions, what will happen if I want to integrate them, and so on. So please look into some of the problems given in the book, and you will see that all these problems are trivial, because they will just come about using the properties, the corresponding properties of the vector functions, or sorry, the real valued functions. Okay, so please solve some problems and discuss during the tutorial, and this I will stop today here, and in this week I will have one more small lecture, and there you will see that using the idea of derivative and so on, we will be able to introduce some new properties and some important concepts which we can address, okay, or some important problems we can address. So we will slowly build and keep recalling whatever is required in the process. Okay, so see you, bye.